In this lesson, we'll go through the trends in ionization energy across the periodic table. We'll look at the trends down the group and across the period. So if we begin with the trend in ionization energy down the group, I'll write down group 1. So as we go down this group, the size of the atoms increase. So lithium has 2 shells. So this is the first shell of lithium and this is the second shell. For sodium, it has 3 shells or 3 quantum shells. Potassium has 4, rubidium has 5 and cesium has 6. Now if we go down the group, the distance between the outermost electrons, so for lithium it was this electron over here, this is the outermost electron. For sodium we have 2 here, 8 here and 1 here. This is the outermost electron for sodium. So the distance between lithium's outermost electron and its nucleus is smaller than sodium, and so on. So as we go down the group, the distance between the nucleus and the outermost electron increases. And if that happens, the energy of the electron increases, since the energy of the electron depends on the distance it is from the nucleus. Also, if we go down the group, the shielding increases. Shielding is basically repulsion from the innermost electrons. So for lithium, if we think about its outermost electron, the red one, it will be repulsed by the inner electrons. So these 2 electrons are also negatively charged. This one is also negatively charged. The same charge repulses. So the inner electrons over here causes a repulsive force on the outer electron. If we go from lithium to sodium or potassium, which have more electrons in its inner shell, so this is sodium. Now for sodium, its outermost electron faces more repulsion from the inner electrons. So the outermost electron is more weakly attracted to the nucleus. So it is easier to get this outermost electron out of this electron cloud, causing the ionization energy to decrease. Now you can say that as we go down the group, the nuclear charge increases, or the number of protons increase. If there are more protons, the electrons should be attracted more strongly to the nucleus. But however, these 2 points over here outweigh the effects of nuclear charge. So in overall, it becomes easier to pull the electrons out. So it becomes easier to get this electron out of its shell as we go down the group. Therefore, the ionization energy decreases down the group. Now, this is the trend down the group. Now coming across the period. So we have period 2 over here. Now if we go across the period, so from lithium to neon, the nuclear charge increases. The nuclear charge is the number of protons. So we go from 3, 4, 5, 6, 7, 8, 9 up to 10. So as we go down the group, go across the period, the nuclear charge increases. So the electrons are more strongly attracted to the nucleus. The shielding or repulsion from the innermost electrons remain almost the same, since they are in the same period. So if I have lithium, it has this electronic configuration. If I look at beryllium, it has 2 and then 2 more. Here the outermost electrons have almost the same repulsion from the inner electrons. The number of inner electrons are the same. So each outermost electron has 2 inner electrons. So shielding is almost the same. The repulsion from inner electrons are almost the same as we go across the group. Also, as we go across the group, the size of the atoms decreases since the electrons are more attracted to the nucleus, so they tend to come inward, causing the atom to be smaller. So if we take all these factors into play, the nuclear charge increases or the number of proton increases. This causes the electrons to have a higher positive charge to be attracted to, causing it to be more strongly attracted. And if we look at the repulsion from inner electrons, this is almost the same. The size of the atom also decreases. If the size of the atom decreases, the outermost electrons will be closer to the nucleus. So this is the nucleus. So instead of the outermost electrons being in the white region, it will be in the blue region. So it's closer to the positive charge or the nucleus, so it will be more strongly attracted to it. So across the period, the ionization energy generally increases. We have to say generally because we will be learning about two exceptions to this. So if we draw a chart of the first ionization energy of the period 2 elements, we'll get this. Now if we look here, we see a general upward pattern. However, there are two exceptions to this. One is when we go from beryllium to boron, and one is when we go from nitrogen to oxygen. Now there are two different explanations to why this to happen. So for the first case, if we look at beryllium's electronic structure, we'll get 1s2, 2s2. So the outermost electron is removed from the 2s subshell. However, if we look for the electronic configuration of boron, we'll have 1s2, 2s2, 2p1. Here the outermost electron is removed from 2p. In this case, the outermost electron was removed from 2s for beryllium, and for boron it was removed from 2p. Now the energy gap from 2s and 2p is big enough for the partial shielding. So the 2p electrons are outside the 2s electrons. So if the 2s electron is somewhere over here, the 2p electron will be somewhere along here. Close but a little farther away. So it will face more repulsion from the inner electrons than beryllium does in 2s. This causes the 2p electron to be less strongly attracted to the nucleus, causing it to have a lower ionization energy. We say partially shielded over here because the shielding is from a subshell and not a whole shell. So in normal cases, we say shielding about the third. So if I have something with 3 electron cloud, so we say the third electron shell is shielded by the first and the second one. However, we are saying here that the 2p subshell is shielded by the 2s subshell. So when we are talking about subshell, we say it's partial shielding. And now for the second exception in this trend, which is between nitrogen and oxygen. Now if we look at nitrogen and oxygen, nitrogen is 1s2, 2s2, 2p3, while oxygen is 1s2, 2s2, 2p4. So the difference is in the 2p subshell. So if I draw the 2p subshell for both of them, this is the 2p. For nitrogen, this is the 2p subshell. And for oxygen, we have this. When the 2p orbitals are half filled, it's harder to remove the electrons since they don't face any repulsion in their orbital. However, in case of oxygen, this 2p orbital, this one over here, has 2 electrons. So the second electron will face some repulsion from the first electron occupying the same orbital. So this will face repulsion from this electron over here. So this electron over here will be easier to remove than one of the 2p electrons from nitrogen because they are unpaired. So simply put, paired electrons are easier to remove. So this causes this exception. So this is the reason behind this dip, that oxygen's paired 2p electron is easier to remove than nitrogen's unpaired 2p electron. We'll see the same trend in case of period 3 elements. So instead of lithium, we'll have sodium. Instead of beryllium, we'll have magnesium. Instead of boron, we'll have aluminium. Instead of carbon, we'll have silicon. Instead of nitrogen, we'll have phosphorus. Instead of oxygen, sulfur. Instead of fluorine, chlorine. And instead of neon, we'll have argon. The same general shape will be exhibited by. And in case of that, instead of the 2p electron, we'll talk about the 3p electron and 3p and 3s over here. Now we'll move on to the trends of successive ionization energies. So what do we define as successive ionization energy? It basically means that if we keep removing all the electrons of an atom one by one, where the element is in its gaseous form and we have 1 mole of it, then their energy and their ionization energy for each one together is known as the successive ionization energies. So if I look at an example for oxygen, its first ionization will be oxygen gas turning to oxygen plus gas plus 1 electron. Even if I had stuff which are normally solid, so magnesium for example, even that will have to use as a gas, since the successive ionization energy is strictly for 1 mole of gaseous element. So even here we are not writing O2, which is the usual form oxygen stays in. We want this form, pure O. No molecule, just the element in its gaseous form and 1 mole of it. So this is the first ionization. For oxygen, the second ionization would be O plus becoming O2 plus and 1 electron. The third ionization will be O2 plus becoming O3 plus. The fourth one will be 3 plus becoming 4 plus, and so on. Now if I think about what's going on in successive ionizations, between the first and second, the oxygen is becoming more positive. So in this case there were 8 positive charges for 8 electrons, so 8 protons or for 8 electrons. Now there are 8 protons for 7 electrons, and if we go on 8 protons for 6 electrons, we are not removing any protons here, we are just removing electrons. So in this case we have 8 protons and 5 electrons. Here the ratio of electrons to proton is decreasing, so there are less electrons for each proton, so each proton can attract the electrons more strongly. In this case you could think 8 protons were attracting 8 electrons with 1 units, so they had 8 protons had a total of 8 units of attraction. So these aren't actual stuff, I'm just trying to visualize this concept. So even now if I have 8 units of attraction, I have 7. In this case I had 8 things to attract, so I could only use 1 per each. Now I can use more than 1 to attract each electron. Over here, if I have 8 units, I have even less things to attract, so I can use more. So basically, if I have the same money to buy less things, I can pay more to get. Or I can think of the protons as a company. So the company has the same profit. So this is 8. They have the same profit, but as we go down, initially there were 8 employees, now 7, then 6 and 5. So if I make the same money and have less employees, I can pay more to each employee. In this case, something similar happens. So each proton has less electrons to attract, so they can attract them more strongly. So the electrons are more strongly attracted to the nucleus, which makes it harder to take out from the electron cloud. So as we go across each ionization, so from the first to the second, the attraction between the protons and the remaining electrons will increase in the way I just said. So more energy will be needed to overcome the stronger attraction. Now there are spatial jumps. So when we go from shell 2 to shell 1, so for magnesium in case, I'll show sodium. Magnesium will be too big. So sodium has this electron. Oh, I can do magnesium as well. I'm doing it with magnesium. Now for sodium, the first electron that is removed, or the first ionization, happens from here or here. So one of those electrons. So I'll assume this is the first electron that's ionized. After that, the second electron will be ionized from the same quantum shell. So they have the same shielding, just a stronger attraction to the nucleus due to the nucleus having the same proton number, but there being less electrons now. Now if I remove this, the third ionization will be from an inward electron shell. So now the third ionization will happen to any one of the electrons in this shell. So the second ring. Now the third quantum shell has no electrons left. The next electron will be removed from here. Now when we go from the third quantum shell to the second, there is a big change in the energy level. There is a huge change in energy level between two quantum shells. So there's a big jump over here when we go from the third shell to the second one. The distance in between the electrons and the nucleus decrease over here when we go from the third shell to the second one. So the electrons in this red second shell are more strongly attracted than the ones that were in the blue third shell. So now there will be a big increase. So for magnesium, the first ionization, if I draw a graph beside it, the first ionization will have a small difference between them. Now, however, going to the third one, there will be a big increase. And then the next 8 electrons, so so until these electrons are all removed from the second shell, they'll also rise at a steady level. So 1, 2, 3, 4, 5, 6, 7, and 8. After we remove 8 electrons from here, we have to remove from the first quantum shell. So this will again see a big jump and then go on. So this, if we join them together, we'll have this, and then a big rise, and then stable again, and then another big rise over here, and then stable again. We cannot continue after this since we'll have 0 electrons left after this. So that covers the ionization energy trend and the trend in successive ionization energy. And for a quick note, so the highest Xth ionization energy, so the highest first ionization energy or the highest second ionization energy will be for the X plus first element. So the highest first ionization energy will be from the second element or helium. The highest second ionization energy will be from the third element, which is lithium. The highest third ionization energy will be from the fourth element, which is beryllium. The highest fourth ionization energy will be from boron, and so on. And that's it for today.